So I hope for mass concentration, you did something like this. Actually, you took this 38.7 and then you divided it by 1.25 itself, and you got your answer, right? Is that so?
Yes, sir.
And what was the answer exactly? Sorry, what was the answer?
Just a second, sir.
Yeah, sure. Take your time.
Yes, sir. My answer was for mass concentration, it was 30.96.
13.96. Just a second. 30.96, if I'm right. Correct?
Yes, sir.
Okay, good. That is in gram per decimeter cube units. And for molar concentration, what MR did you calculate for CH3COONA?
Sir, 82.
Okay, let's see it again. That was 12 plus 3 plus 12 plus 16 two times, or you can add 16 twice, plus 23. And the whole came out to be 82.
Yes, sir. It is 82.
Sounds about right. Okay, so the whole thing is 82. So that means you divided 38.7 with 82, and then you multiplied it by 1 over 1.25. You can do 1 over 1.25 if you have the decimeter cube section, or if you have the centimeter cube conversion, you can divide it by 1000 over 1250, but it really stays as same. So it's entirely up to you whether you do the conversion or not. Actually, conversion takes more time, so I go with this kind of stuff. Sometimes the student tend to do it in this way. They write 38.7 over 82 on top as a numerator, as a whole thing, and then they write 1.25 as a denominator. Well, whether you write it this way or you write it that way, it really means the same thing as per the rules of mathematics.
Yes, yes, sir.
Okay, so the answer to this one was,
Sir, what I did here was moles divided by volume equals to mass divided by mr multiplied by I wrote 1,000 divided by volume centimeter cube, and so rather than writing one, I wrote 1,000.
okay, let me tell you something, that if you, on the other side of multiplication, I hope you took this one as 38.7 and this one over 82, then for the multiplication section, let me read it, it's a little messy, little difficult to understand. So when you're writing 1,000, then you're supposed to write the volume in centimeter cube. Remember, the formula was in centimeter cube, and it's written right over here in the center of the page. Okay, so if
So I
you're
wrote
doing
it
like
in
that,
12.50.
so this multiplied by 1,000 becomes 1250 centimeter cube. So you need to write
Yes, sir. I wrote
1250
that.
over it. then you have done it perfectly. There is nothing wrong with this.
Okay.
Okay.
The
So
answer is 0.38 moles per decimeter cube.
0.38 mole per decimeter cube. But that's just two significant figures. We need a third significant figure.
Okay, then it would be 0.378.
0.378. Now that seems about more accurate. So let's erase it. Instead of this, I would rather say that we go with three significant figures. So it's 0.378 mole per decimeter cube. And yes, that's the correct answer. This one is correct too. So you actually have a multiple ways of doing the same thing, whether 1000 over 1250 or 1 over 1.25, or simply this thing over divided by 1.25. It's entirely up to you. Remember, whether you write it this way or this way or this way, remember, the answer in every way is going to be the same. That's the best part about mathematics. Playing with numbers, if you're doing it right, your answer is supposed to be the same, whichever method you choose.
Okay.
Okay, so that's three right there. So I'm going to stop sharing for just a minute and we're going to get to the other slide. We're going to solve those questions you find a little bit more confusing than this one. Yeah, just a minute. All right, so let's get on with these questions. Now, I hope you have the picture in front of you, the picture which specifically says the formula. So can you repeat that formula out loud for me? The interconversion formula, what did that say?
So um, it's mass divided by volume.
Hmm? The interconversion formula, the one at the bottom of the page. Do you want me to take you to that page? Okay, let me take you to that page. Just a minute. Okay, so that concentration diagram in which I stated the types of concentration, that specific page at the bottom, you would see the concentration interconversion formula. And this is a very specific formula that molar concentration in mole per decimeter cube is equal to mass concentration, which is in the units of gram per decimeter cube, divided by the MR of solute in gram per mole. That's the formula you were supposed to use for these two questions. So I'm going to use the same formula over there. All right. So getting back to that, let me rewrite the formula on the top of this page so that it's not difficult for you. So when we have the molar concentration in the units of mole per decimeter cube, that can be taken from the mass concentration if it's in the units of gram per decimeter cube, when it's specifically divided by the MR, and the MR should be of solute only from the periodic table, which is usually given in the units of gram per mole. Now take a look, we'll easily cancel out gram and gram, the mole goes as numerator, decimeter cube comes as denominator, so it becomes mole per decimeter cube. So the first question, you are given with this gram per decimeter cube value. NaOH, the name is given, you can easily find out the MR, and then you can divide these two values to get your molar concentration. Can you try it now? Why don't you go ahead and try it? So now you know that it's 10 grams per decimeter cube, and since it's NaOH, so the MR is going to be, for Na, the periodic table says 23, for O, the periodic table says 16, for H, the periodic table says 1, the whole thing comes out to be 40, so it's really 40 gram per mole. So I would easily be able to cut these values and I would be able to come up with an answer in mole per decimeter cube unit. So what is that answer? Go ahead, try to solve this one by yourself. You'll know what I was talking about.
Sure, 0.25.
0.25 mole per decimeter cube to make our answer
0.250.
perfect. That's what I wanted you to say.
Okay.
Great.
Sir, yeah, that's the mistake I made. I wasn't using this formula. I was using the other formulas that were given, such as mass concentration and the molecular concentration, and I totally forgot about the interconversion formula. So yeah, and now I understand, sir, how to solve this. I could solve it now.
Then go ahead, solve question number two. However, in question number two, you will require to rearrange the formula a little bit. Go ahead. If you can solve it now, I think you would easily be able to do question number two correctly. I mean, take your time. When you're done, let me know.
Yeah, 5.6 grams per decimeter.
Okay, great. And I hope you took this one as 0.1 mole per decimeter cube over here. And then the mass concentration was supposed to be here. So that was in the units of gram per decimeter cube. Now you took the MR onto this side instead of dividing over here, you took the MR over here. And I hope you calculated it to be 56. That's why your answer is coming out to be 5.6 um, gram per decimeter cube. In order to convert it into three significant figures, it's 5.60 gram per decimeter cube. I hope you have done it in the exact same way, right?
Yes, sir. Yes, sir.
Great. Then you know how to handle these kind of questions. Now,
I could do another if it's possible.
good, great. And I am pretty hopeful that you're going to get them right. Okay, so remember a couple of days earlier when we were doing some yield questions and you asked me some more questions about those. I intentionally stopped you by giving you any examples more to solve because I wanted to add some more material to those kind of questions. Yes, we are definitely going to solidify those concepts, but this time what we're going to do is that instead of just talking about mass or volume of gases, we are also going to add concentration to those kind of questions because that's what Cambridge does most. When you're going to look at the past papers, you'll understand that they tend to involve concentration with almost every other question they go with. Since they pay so much emphasis to concentration questions, so now we are going to practice yield questions again. This time, we're going to go with concentration. Okay, so let's try a yield question by throwing in concentration questions as a part of yield questions. Okay, let's try take an example first, and then you would be able to solve after the first example. You would definitely be able to solve the next questions all by yourself. So just all right. Let's go with first example. Calcium carbonate, the formula for which is CuCO3, 28.7 grams. Actually, let's not quote this value like this. So there you go. You have calcium carbonate in excess, which reacts with 0.1 mole per decimeter cube of 25 cubic centimeter HCl. You have the molar concentration and you also have the volume of HCl, but you don't know the number of moles, which you're definitely going to find out from the formula of molar concentration, right? Then it actually produces 25 cubic centimeter of carbon dioxide gas. This is the actual yield, 25 cubic centimeter of CO2. So we're going to find out the predicted yield, Py, and then we're going to calculate the percentage yield of carbon dioxide produced. You already have the equation is balanced as per the IGCSE pattern. I am going to write and mention the steps for you, all four steps actually. So you are going to work in those footsteps, use the formula or the ratio parts and find out the percentage yield. So the first part is to calculate moles of HCl reacted. And since HCl was present in the form of a solution, so you need to find out with the help of the concentration formula. Moles, then we have number 2, moles of CO2 produced. That too will be found in moles. Remember, the method is pretty much simple. First step is always the formula step, second step is always the ratio step, third step is the formula step, third step is usually also the answer to the predicted yield. So volume of CO2 produced. Now the formula in the first step is going to be very much different from the formula in the third step. And the final step is going to be percentage yield, which would be actual yield, which is 25 cubic centimeter as given in the question, predicted yield, and predicted yield, as I've said earlier, is usually the answer to part 3 multiplied by 100. There you go. Remember, first step is formula, and the formula you're going to use is the molar concentration formula. Take your time. If you get stuck at any point, or as soon as you find an answer to a step, let me know. Make it a part of recording. This is going to be concentration, which is equal to moles over volume. Remember, volume has to be in decimeter cube. That was the main formula. So we tend to use this formula for this question. Why? Because the concentration is already given 0.1. The volume is already given 25, but unfortunately that is in centimeter cube. So you need to convert that into decimeter cube first. So before you put it over here, divide it by 1000 to convert it into decimeter cube, and then you can go on with this. So what I actually ask my students to do is to do something like this. I'm going to raise this whole thing up. I'm going to rearrange the formula for your own ease. So moles are actually going to be equal to concentration multiplied by volume. The volume is in centimeter cube, so it's better that you divide the whole thing by 1000. Okay, so for the second step, I would suggest that you go with the ratio of HCl, ratio CO2. You know what to do with the numbers over here. For the third step, volume is equal to moles. Since we're talking about a gas, so the formula changes. You can't use the same formula as of step 1 in step 3 because step 1 is for solution and step 3 is for a gas. So moles into molar volume. Now you know the value of molar volume is for same for all gases on the planet, so this should be easier for you. And also remember this part is actually giving you the answer to Py. Part 3 is giving you the answer to Py. So whatever you have as Py, that answer to step 3, that's Py. Ay is already given in the question as 25 cubic centimeter. There you go. You can find out percentage yield. Now you take your time, solve part first, and then let me know what your answer is. I can wait.
Moles.
So your answer, you multiply it by 0.1 concentration divided by 25, and that 25 is divided by 1,000. So your answer comes out to be, I guess the calculator should give you 2.5 into 10 raised to the power minus 3 moles, something like this. Is it?
Yes, sir. Yes, sir.
Because in standard notation, it would be something like this. Otherwise, you may also write 0.0025. So it's basically the same thing. And just let me confirm the same thing. Yeah, 0.0025 or 2.5 into 10 raised to the power 3 is basically the same thing. So that's number of moles of HCl that reacted. So 2.5 into 10 raised to the power minus 3. I'm starting to think I might have written a greater value of carbon dioxide than required, but let's go with it. Even if my calculation has been wrong with mental maths at one point, still it should give us the right answer to the scenario. So moving on with step 2. Take your time. When you're done, let me know. You're supposed to do it with a ratio. So the numbers for HCl and CO2 in the equation are 2 and this 1. Yeah, so it is 2:1. And then the number of HCl are actually 2.5 multiplied by 10 raised to the power minus 3 over here. And we need to find this x. That tells us that x should be equal to 2.5 multiplied by 10 raised to the power minus 3 divided by 2. When we divide it, the answer comes out to be 1.25 multiplied by 10 raised to the power minus 3. Check it out. Is this correct? Because I'm doing it mentally. I don't have a calculator on me.
Yes, sir. Yes, sir. I forgot to put the point. Yeah, it is 1.25 multiplied by 10, the power of minus 3.
Great. Which means we can come to the next formula. Now, since we know that the value for molar volume for all the gases on the planet is what? Molar volume. Do you remember the value to molar volume for all the gases on the
Yes, sir.
planet?
It's 42. It's 42.
No, it's 24.
Yeah, sorry,
It's
24.
24, yes. So what happens when you multiply this 1.25 into 10 raised to the power minus 3 with 24?
So it would be 0.03.
I need another significant figure, 0.03. Is there anything up?
0.030?
Okay,
Because
so
no
0.030.
0.0. It's just
Okay,
0.03.
yeah, that's good enough. 0.030. Okay, and that is decimeter cube. Okay. Now, for my own ease, I can either convert either this 25 into decimeter cube or this 0.03 decimeter cube into centimeter cube. Either one of this should work fine. Okay. So actual yield is 25 cubic centimeter. Of course, I'm going to divide that by 1,000 before I put it over here. And then this 0.03. 0, and that is supposed to be multiplied by 100. So what is the answer to this one?
So the answer is 83.33.
83.3%. Okay, this is 0.025, right? The numerator is 0.025. So when you divide it by 0.03 and when you multiply it by 100, the answer comes out to be 83.3%. Yeah, that seems about right. So our yield is 83.3%. Okay, yeah, I never quoted a wrong value. My value is too close to the answer. Well, I was expecting a little bit of a lower yield than 83.3. Okay, so does this make sense?
Sir, can you repeat the last part you said?
Yeah, that was about my calculation.
Oh,
Before writing a question over here, I actually try to mentally calculate the answer, what the answer is going to be. Before even I write the steps, I tend to calculate the percentage yield all by myself. So when I was mentally calculating it, after I was done writing the first two lines of the question, when I didn't even write the equation yet, I was expecting this percentage to be somewhere around 43% or 40%. Well, it turned out to be 83.3%. That's what I was talking about. That
okay,
it's
all right.
far higher than my expectation. But since I'm calculating mentally, so I am a little bit bound to make mistakes. Calculators are very good in calculation, and mental calculation sometimes gets you the wrong value. But I think
Yes, sir.
yeah, tend to keep calculating mentally. I love that part about math. Okay, so getting back to this, I hope this all makes sense, right?
Yes, sir. Yeah.
So if I go by a similar question in which I change a little bit of values, a little bit of chemicals, of course, we're not going to react it with the same acid or use the same compound or produce the same gas. But if we go with the same steps, these four steps, would you be able to solve it?
Yes, sir. I hope so. Yeah.
Good, great. So what I'm going to do is that I'm going to prepare the next whiteboard. I'm going to write the question, but before I do that, I'm going to send you this picture on WhatsApp. So you have the picture in front of you, and wherever you need guidance, this question is going to guide you for the next part, of course. Okay. Well, actually, why don't we do it like this? I can send you the picture right after uh, this whole class, and I'm going to just write the question on the next uh, whiteboard. Just give me a minute to get back to you. So, question number 2, a similar question. Sodium thiosulfate, a substance that is commonly present in labs and has really big crystals, even bigger than what we commonly use for sugar nowadays. The formula to which is Na2S2O3. In excess, reacts with 0.01 mole per decimeter cube of 12.5 cubic centimeter HCl as Na2S2O3. And I'm going to already balance the equation out for you. When reacting with 2 HCl produces to NaCl for us. It also produces a toxic gas, SO2. Along with that, it produces sulfur as yellow precipitate, yellow solid. And since we call this an information of solid that tends to settle at the bottom of the beaker or the apparatus we try to perform our experiments in, and along with water. So only 1.25 grams of yellow PPT of sulfur were actually produced. Now, I specifically chose this reaction and this experiment because it's already a part of IGCSE. When you're going to open up your book to chapter number 7, there is a specific uh, technique for rate of reaction that we're going to use to study time and rate of reaction, or how they are probably actually proportional to one another. We're also going to study what temperature does to the speed of a reaction. There you're going to see the same equation, the same yellow precipitates. Teachers actually tend to perform this experiment in lab as well, and they sometimes also allow the students to perform it on their own. And the formation of this yellow precipitates is a really good experiment to perform if I talk about in terms of perspective of a student. Okay. So you are supposed to calculate the percentage yield. Again, in the similar way, I am going to chalk out your steps. So your first step would be moles of HCl reacted. And of course, the answer is going to come out as 10 raised to power minus 3 or 10 raised to power minus 4. I mean, the answers will be in scientific notation for the first two parts, of course. And you're going to use the same formula as the previous question. Since you'll be using the same formula, so I am not going to elaborate for part 1 or for part 2 either, since you'll be using the same things. However, for part 3, it's going to be a little bit different, so I will definitely elaborate part 3. Okay.
Okay, sir.
So moles for S produced. And lastly, since uh, sulfur is produced as a solid and not as a gas, so that's why I can't put volume over here. This is what makes the part C different from the part C of the previous question. Since in previous question we were talking about a gas, so we put the quantity of volume over there. And here we are talking about a solid, so we need mass, and for mass we need grams, which means the elaboration of this part tells you that your formula that you are supposed to use is going to be mass, which is equal to moles multiplied by mr. And really, in this case, it's just sulfur, so we'll be using the value of Ar, the relative atomic mass of sulfur, as mr for this question. Okay, that's why I've specified Ar in brackets. Mr is the general term we use, but when we are just dealing with simple elements like this one in reaction, it just produces one single element. It doesn't produce a whole compound in this specific case. So that's why Ar is a more appropriate term to use. And of course, the last part is going to be percentage yield, for which AY is given in the question in the third line, 1.25 grams. PY is the answer to part 3. And of course, you multiply it by 100 to get your answer in percentage. Okay? Since the answer over here to part 3 would be in grams, and also the value of 1.25 is given in grams, you won't require any change of units to put into part 4. So your part 4 this time is going to be relatively very simple. Make sense? So now if we are clear,